This presentation will focus on our research that was published in the Journal of Structural Chemistry entitled Intermolecular Interactions of Liquefied Petroleum Gas Alcohol Mixtures with Phyllosilicates. First, some acknowledgements. This project is the interface of computational and environmental chemistry. In fracking, the phyllosilicates of shale rock are efficiently fractured by water because it disrupts the intermolecular forces holding the grains of these minerals together. Unfortunately, water penetrates pores and minerals, causing shale swelling that decreases wellbore stability and causes the development of breakouts. Recently, a technology of waterless fracking that employs liquefied petroleum gas, a mixture of propane and butane as a drilling fluid. After being injected into a well, LPG can easily be separated from water, removed from the well along with natural gas and oil, and reused later. LPG, being immiscible with water, may potentially have less impact on aquifers. Furthermore, LPG mixtures have low boiling points, so they may be recovered from the well as gases. Also, LPG is available as a byproduct of the natural gas industry. A drawback of this technology is potentially lower efficiency for shale fracturing than water-based drilling fluids. Thus, we propose polyol alcohol additives like ethylene glycol and glycerol, which can be incorporated with the LPG to advantageously increase its polarity. Water was used as the control component for the purpose of comparison. Our first step was to perform individual geometric optimizations of each component configured around each of the phyllosilicate's 6 faces. Then, under the fragment molecular orbital theory, we quantified various types of interaction energies occurring between each fragment of our 36 optimized systems via pair interaction energy decomposition analysis. Finally, we determined how prevalent these interactions were based on certain threshold values that we set while measuring the bond lengths and angles between the component and the phyllosilicate. Here are the more technical details of our computational methods. And here are some visuals that detail the key results and findings. Because propane is so small and nonpolar, it is not selective in deciding which face of the phyllosilicate to interact with. However, because butane and isobutane are large nonpolar molecules and thus have greater dispersion forces and bulkier sterics, they tend to hover around the back face of the phyllosilicate the most. In contrast, larger and more polar molecules like the ethylene glycol and glycerol are more sensitive to the face of the phyllosilicate crystal, and they cling to the back or left faces, which represent cracks and other imperfections in the phyllosilicate crystal. Our future plans are to possibly expand the LPG population by introducing additional molecules of each LPG component into the system, to run molecular dynamics simulations on the systems, and to further study the specific thermodynamics that occur within the system using Cosmos real solvation. For more details, please see our full article in Springer's Structural Chemistry. Thank you.